How to find the speed of light using marshmallows. First thing you want to do is go to your microwave and take out the turntable. I'm also putting this little glass thing in there to raise the marshmallows up a bit, but it's not necessary. Then you want to get your marshmallows and spread them evenly over the bottom of a pan or some kind of container, and you want to put that in the microwave for about 10 seconds. Okay, so those are heating up. Let's explain the actual physics going on here. The important bits of the microwave do some really complicated physics called magic and start spitting microwaves out into the cooking chamber. These microwaves bounce around and form a standing wave pattern, and it's this wave pattern that's responsible for heating things up in a microwave. Microwaves, like all waves, carry energy, and that energy gets transferred to your food, which causes it to heat up. The particulars of this interaction are really kind of complicated, so I'm just going to gloss over them, but the gist of it is that how much heating you get corresponds to the amplitude of the wave at that point. So if you look closely at our standing wave, we have regions that don't change in amplitude or don't oscillate called nodes. At these positions, the microwaves won't heat up the food at all. There's no energy transfer. We also have regions that oscillate between positive and negative amplitude. The center of these regions, where the oscillations are the greatest, are called antinodes. This is where the most heating will occur, and this is the part we really care about. Since we're only heating our marshmallows up for about 10 seconds, we should only see any visible cooking or melting right at the positions of the antinodes, and we can use these positions later to find the speed of light. Okay, so I think it's been about 10 seconds, so let's take out our marshmallows. If you look closely, we have two really obvious melty spots, which is really good. Alright, so to do the actual calculations, we use a very simple formula that works to find the speed of any wave, which is v equals lambda f, where v is the speed, lambda is the wavelength, and f is the frequency, or how many times the wave oscillates from positive to negative amplitude in 1 second. Now, frequency is the easy one. That's given on a sticker on the microwave, and it's usually about 2450 megahertz. If we look back at our wave from earlier, we see that the distance between any two antinodes is exactly half of one wavelength. So if we measure the distance between our melted spots and the marshmallows and then double it, we should get approximately one wavelength. Alright, so measuring that, I get a distance of roughly 6.1 centimeters, and then plugging everything in and solving for speed in meters per second, I get a speed of 2.989 times 10 to the 8th meters per second. If we compare this number to the actual speed of light, which is 2.998 times 10 to the 8th meters per second, we get a percent error of less than 1%. Now, I'm too lazy to figure out the uncertainty of that, but I'd say it's a pretty good estimate for using marshmallows.